In this video lesson, we're going to be able to do four things. First, we'll be able to define an empirical formula, calculate an empirical formula, then move on to defining a molecular formula and calculating a molecular formula. Let's first look at the empirical formulas. First of all, let's go ahead and define. An empirical formula is the lowest whole number ratio of a compound. Please note that this is not a true formula. The only purpose of an empirical formula is to just show ratios. Let's take, for instance, I'm cooking a recipe, and the recipe calls for 1 part flour for 2 parts sugar. Now, what does that mean? Well, what that means is for every 1 part of flour that I'm going to have, I'm going to need double the amount of sugar. So if I were using 1 cup of flour, how much sugar would I need? The answer to that is 2 cups. What if I was using 2 cups of flour? Well, then that would mean I would need 4 cups of flour. Notice how the 1 and the 2 are only there to tell you what the ratio is. It does not mean you are in fact using 1 cup and 2 cups. Let's take a look at an example in the chemistry world. Look at the formula CH2O. This is an example of an empirical formula for the true compound C6H12O6. C6H12O6 is the real compound. In fact, we call that glucose, which you may have heard of before. Glucose is the true formula for that compound. There are 6 carbons, 12 hydrogens, and 6 oxygens. However, notice what the empirical formula is doing. It is setting up the lowest whole number ratio. For every 1 carbon, you will have 2 hydrogens and 1 oxygen. Let's see if that's true. Well, I have 6 carbons, and according to my empirical formula, I should have double the amount of hydrogens, which in fact I do. And oxygen should have the same ratio as carbon, which in fact it does. So notice how the empirical formula is not the true formula, but just sets up the whole number ratio. Now that we know that, let's go ahead and figure out how we determine the empirical formula. The first step to determining an empirical formula is to turn all your percentages into grams. What will happen is all the percentages will be reported to you, and we're going to turn those into grams. The next step after we do that is we will turn our grams into moles. This is going to call for a molar conversion. Once everything's been turned into moles, we are going to divide all the values from step 2 by the lowest number of moles from step 2. The fourth step is to round all the answers from step 3 to whole numbers. These numbers then become your subscripts for the empirical formula. Now notice as you're looking at this, there's a lot of steps and a lot of confusion can happen by simply looking at this. Therefore, we're going to do a few examples together to make sure we understand the concept of empirical formulas. Let's take a look at our first example and have these steps ready to look at as we go through. All right, suppose I tell you that you have a compound that is 75% carbon and 25% hydrogen. You are asked to compute the empirical formula or the lowest whole number ratio for this compound. All right, step 1 tells us to turn our percentages into grams. If we assume that we have 100 grams of this sample, that would mean that 75% becomes 75 grams and 25% becomes 25 grams. Notice how easy the first step is. In the first step, all you do is take your percentages and just change them to grams. Since we're assuming 100 grams of this sample, we can do that. Now, step 2 calls for us to take our grams and to convert that into moles. Let's do carbon first. Where we left off, we said we had 75 grams of carbon. If we want to convert that into moles, we have to divide by the atomic mass of carbon. Carbon's atomic mass is 12.01. By taking 75 divided by 12.01, we get the number of moles is approximately 6.24. Now let's do hydrogen. Hydrogen, we assume that there was 25 grams, and the atomic mass of hydrogen is 1.01. If we take 25 divided by 1.01, our number of moles is approximately 24.75. We have now converted grams to moles. Now our third step calls us to take a look at our moles and divide each mole by the lowest number. Well, out of 6.24 and 24.25, which one is lower? Well, the obvious answer is 6.24 is lower. So what that means is we're going to take both of these answers and divide those by the lowest number, which was 6.24. So for carbon, obviously, the answer we got, 6.24, divided by the lowest number of moles, which was 6.24, is going to give us the number 1. For hydrogen, the answer we got was 24.75. If we divide that by 6.24, the answer we get is approximately 3.97. Now, our steps tell us to convert that into the nearest whole number, which in this case is 4. Now that we know both of those numbers, the fourth step tells us that these are going to be the subscripts for our elements. So for carbon, our subscript was 1, and for hydrogen, our subscript is 4. Therefore, our empirical formula for this compound is CH4. What that means is for every 1 carbon, there will be 4 hydrogens. Let's take a look at another example. Suppose I tell you that you're looking at a specific compound, 52.7% of it is potassium, and 47.3% of it is chlorine. All right, our first step is to turn our percentages into grams. Remember, this is easy. Take off the percentages and simply put grams. So potassium is 52.7 grams, and chlorine is 47.3 grams. Our second step then is to convert those into moles. Let's do potassium first. 52.7 grams of potassium divided by the atomic mass of potassium, which is 39.1, will give us our number of moles. By doing 52.7 divided by 39.1, our number of moles for this is 1.35 moles approximately. All right, let's go ahead and do chlorine. Chlorine, we got 47.3 grams divided by the molar mass, which is 35.45, will give us our number of moles for chlorine. Take 47.3 divided by 35.45, and our number of moles is approximately 1.33. Now our third step is to take our answers that we got, 1.35 moles for potassium and 1.33 moles for chlorine, and divide both of those numbers by the lowest number of moles. Well, they're pretty close, but technically the lowest number is 1.33, and therefore we will divide both answers by 1.33. If we do that, we get for chlorine, obviously 1, and for potassium, we get an answer very close to 1, approximately 1.02. Now, since our steps tell us to round to the nearest whole number, even though potassium is a little higher, we're still going to round that to 1. What that means is our empirical formula is a 1-to-1 ratio. And therefore, our empirical formula is 1 potassium to 1 chlorine, or KCl. Notice how the metal gets placed first before the nonmetal. Now that we know how to calculate empirical formulas, we're going to use this information to guide us in the last step, which is the molecular formulas. Remember, the empirical formula was only the lowest whole number ratio. The molecular formula, however, is the true formula for the compound. If we take a look at the example we looked at before, remember CH2O was the empirical formula. It only told us the ratio. For every 1 carbon, there would be 2 hydrogens and 1 oxygen. But that was not the true formula. That compound technically does not exist. It's only a ratio. The true compound in this case is C6H12O6. This is a compound that does exist. And so in this step, we're going to learn how to get from the empirical all the way to the molecular. Now, the good news about calculating molecular formulas is that the steps are a lot easier than what it was for empirical. Your first step is to determine the molar mass of the empirical formula. This implies that you'll need to figure out what the empirical formula is. Sometimes the empirical formula is given to you. Other times, you'll have to figure it out. In either way, you'll need to determine what the molar mass is for the empirical formula. The second step is you will divide the molar mass of your true compound, which must be given to you, by the molar mass of the empirical formula that you found in step number 1. When you divide those two numbers, you'll round the number that you get and multiply every subscript in your empirical formula by that number. Now that we know the steps, let's look at a few examples. All right. Suppose you are looking at a formula in which you know the empirical formula is NO2. It also tells you that the molecular mass or molar mass of this compound, of the true compound that is 92 grams per mole. The question is, what then is the molecular formula? All right. Our first step is to determine the empirical formula and figure out what its molar mass is. Well, the good news is it already has given us the empirical formula. The empirical formula is NO2. What that means is our true formula, whatever that is going to have a 1 to 2 ratio. For every 1 nitrogen, there will be 2 oxygens. All right, since we have the compound, let's figure out what its molar mass is. Our empirical formula is NO2. That's been given. We have 1 nitrogen and we have 2 oxygens. Nitrogen is 14.01 and oxygen is 16, but there's 2 of them, making it 32. If we add 14.01 and 32, we get our molar mass for our empirical formula. Our second step then tells us to take the molar mass of the true compound, which is given, divided by the molar mass of the empirical formula. The molar mass of the true compound has been given to us, 92 grams per mole, and so that will go on top. We'll divide that by the molar mass of the empirical formula. We just figured that out in step 1. It is 46.01 grams per mole. When we divide these two numbers together, 92 divided by 46.01, we get an answer of approximately 1.999. That can be rounded to the next nearest whole number, which is 2. The final step is step 3. And in step 3, it tells us to take our empirical formula, which was NO2, and multiply every subscript in the empirical formula by the number that we got in step 2. which is the number 2. That means nitrogen originally had a subscript of 1. 1 times 2 would give me 2. And therefore, that's my subscript right there. Oxygen had an original subscript of 2. If we multiply that subscript by 2, we get 4. And therefore, the subscript is 4. The true formula for this compound then is N2O4. Notice that lines up with what we got for our empirical. Remember, for every 1 nitrogen, there should be 2 oxygens, or double. And that is in fact the case. Let's go ahead and take a look at another example and make sure we understand. Suppose I give you a compound in which the empirical formula is CH2. In addition to that, we know that the molar mass of the true compound has been given as being 70 grams per mole. Given this information then, what is the molecular formula for the true compound? All right, let's go ahead and go through our steps. The first step is determining the empirical formula and what its molar mass is. Once again, empirical formula has been given. All we have to do is figure out what the molar mass is. CH2, we have 1 carbon at 12.01, and we have 2 hydrogens. 1.01 times 2 gives us 2.02. By adding these together, we get our molar mass. In this case, 14.03. Our second step is to take the molar mass of the true compound and divide it by the molar mass found in step 1. Our true compound has a molar mass of 70 grams per mole. We're going to take that molar mass and divide it by the molar mass of our empirical formula, 14.03. If we take 70 divided by 14.03, we get an answer of 4.99. Rounding that, the answer is 5. Finally, step 3 has us taking our empirical formula, which was CH2, and timesing every subscript in it by 5. Since the subscript for carbon was 1 times 5, that gives us a subscript of 5. The subscript for hydrogen was 2, times that by 5 gives us a subscript now of 10. And therefore, our true formula would be C5H10. This concludes the video lesson on empirical and molecular formulas.